Hello! In this video, I'd like to talk about a really neat system of mathematical notation. Now, different mathematicians use different mathematical notation, and so if you're reading a particular text, make sure you check at the beginning to see what the notation being used in that text actually is. And similarly, if you're writing a particular text, even if it's just writing out a homework problem, make sure that the audience, your professor, knows what the notation that you're using in that text is. Don't just assume that they know the notation that I'm presenting in this video. A very common set to talk about is the set of the first n natural numbers. Mathematicians from set theorists to combinatoricists, all sorts of mathematicians want to talk about this set. And a very nice notation for it is to just refer to this set here as the number n. For instance, we can refer to the set 0, 1, 2 as the number 3. This is unlikely to lead to confusion because it's usually clear from context whether an author is referring to a set of natural numbers or a single natural number, although not always. In some contexts, I've seen this number here have square brackets around it or be bold to indicate that it's referring to the set and not the actual number. But very often in a logical context, I've seen this set be referred to just as the number 3. And that's partly due to something called von Neumann ordinal notation, which I'll talk about in a future video. The notation for sets that I'm talking about in this video also sometimes applies for mathematical structures as well. For instance, there actually aren't that many structures on a set like this. I guess you could have like a finite ring, but I've never seen this notation being used when referring to a particular finite ring. I have seen this notation being used, however, when referring to linear orderings. The set 0, 1, 2 is a 3-point linear ordering. It's just 3 points. All 3-point linear orderings are isomorphic to each other, and this is just a convenient notation to refer to the 3-point linear ordering. A very common type of notation in mathematics is the Cartesian product notation. I've always seen it written with a cross product and not other sorts of multiplication notation. But it's fundamentally, there's a reason why, and we'll see why in just a moment, there's a reason why we use multiplication notation to refer to the Cartesian product. But anyway, we use the notation A cross B to refer to the set of all pairs of something from A and something from B. Already one of the really basic reasons why we want to use multiplication notation for this is because it multiplies the sizes of sets together. Here I have the cross product of the sets 2 and 3. Remember that 2 is the set 0, 1, and 3 is the set 0, 1, 2. And so what we're looking at here is the set of all pairs where the first element is something from the set 0, 1, and the second element is something from the set 0, 1, 2. And we see that the size of this set here is 6. The size of the cross product is the product of the sizes of the original sets. Of course, there's no sense in which this set here is equal to 6. It's just the same size as the set 6. But that's a good enough reason to want to call this a product, and we'll see some other reasons later on. And we can combine this cross product notation with other set notation that we've seen before. We refer to the set of natural numbers as either this blackboard bold n, or as omega, it depends a lot on the context. This notation of using kind of a double line to write a particular letter is called blackboard bold, and it comes from the fact that it's really hard to write bold characters on a blackboard, or to type them on early typewriters. And so other notation had to be adopted, but we used to use bold to indicate these sets of numbers, and now we typically use this blackboard bold notation for these sorts of sets of numbers and not much else. We use a Blackboard bold Z to refer to the integers, the word number starting with a Z, of course. We use Q to refer to the rationals, of course, quotients, and the letter R for the real numbers. For instance, you may have seen the notation R cross R. This is just the set of all pairs of real numbers. And because we already have some structure on the set of real numbers, for instance, we know how to add two real numbers together, we can extend that structure to R cross R. And the typical way to take a binary operation like addition or multiplication and extend it to pairs is component-wise, right? In order to add together two pairs, we simply add together the first components of the pairs to get the first component of the sum, and we add together the second components of the pairs to get the second component of the sum. And what this does is it gives us a group structure, right, a notion of addition on these pairs, and we can also extend it to a notion of a vector space, right? This is how we add together two vectors in two-dimensional space. Oftentimes you'll see this notation here being used for the set of two-dimensional real vectors. And this is essentially what we have here. I've just written them slightly differently. You may also have seen the Cartesian product being used to talk about sets of points in space. We can use this notation here, here being, of course, the interval from 0 to 1 inclusive. And if we take the product of that with itself, that's going to be the set of all pairs where A and B are both in that set. And visually what this looks like in space is this particular square here, right? It's the set of all points whose x and y coordinates are between 0 and 1 inclusive. So we also include the boundary of the square. And of course we can change this up. For instance, if we wanted to replace this here by the real numbers, we're looking at the set of all pairs where the x-coordinate is still between 0 and 1 inclusive, but the y-coordinate is just any real number. And that's going to look like this infinite vertical strip here. We can also use Cartesian product notation to refer to linear orderings. The integers have a natural linear ordering structure on them. 2, right, the set 0, 1 also has a natural linear ordering structure, right? It's just the 2-point linear ordering. And when we take the product, we're going to get the set of all pairs of the form some integer comma 0 or some integer comma 1, right? Some integer followed by some element of the set 0, 1. And the convention, and this takes a little bit of getting used to, is to order these in what's called reverse lexicographic ordering. That is, it's kind of like the way that you order words in a dictionary. You start with the first letter, and then the second letter, and then the third letter, but it's in reverse. You sort by the last character first, and then the first character if the last characters are the same. For instance, if we wanted to know whether 2, 0 was greater than or less than 3, 0 in this set here, we first look at the last characters. They're the same, so then we look at the first characters. Those are different, and so the one with the larger first character is larger. On the other hand, in order to determine whether 2, 1 is larger than or smaller than 3, 0, again, we first look at the last characters, but this one has a larger last element, and so this one is actually larger than this one. And so if we list out all of the elements in appropriate order, we first list out all of the elements that end with a 0, and then we list out all of the pairs that end with a 1. And so what we have here is kind of like a copy of the integers followed by a copy of the integers. It's kind of this weird infinite thing that's not only infinite on the ends, but also infinite in the middle. And this is really neat. It's really useful to have easy notation for referring to infinite linear orderings that are doing interesting things like this. And another way of thinking about this is that we've actually taken the 2-point linear ordering and we've replaced each point by a copy of the integers. So there's all sorts of situations in mathematics where we want to talk about the set of all pairs where the first element is from one set and the second element is from potentially a different set. I want to take a moment to note that A cross B and B cross A are slightly different from each other. A cross B, here is the set of all pairs of the form something from A followed by something from B. And B cross A is, of course, the set of all pairs something from B, comma, something from A. And oftentimes that doesn't make a difference, right? We can just switch the order within a particular pair, and that's perfectly fine. Right? If you switch the x and y coordinates of your vector, you have to remember that you did that, but it doesn't change how the vectors work. In either case, for instance, you just add vectors component-wise. Although sometimes these are different. When we were talking about linear orderings, the cross product, the ordering depended on the order of the elements within the pair. Right? We ordered based on the second element and then on the first element. So it's not always going to be the case that A cross B and B cross A are essentially exactly the same thing. For instance, the ordering on 2 cross Z looks something like this, and it's actually not the same ordering as the ordering on Z cross 2. You can't even pair up the elements. What you can do actually is pair up the elements of 2 cross Z with Z itself, and those two orderings are the same. So just as with the rest of mathematics, sometimes the order that you multiply things in matters and sometimes it doesn't. And you might ask, well, okay, multiplication is commutative sometimes, and so, it's interesting to ask whether Cartesian products are commutative, but what about associativity? Is the Cartesian product associative? Is it the case that A cross B cross C is the same thing as A cross B cross C? And the answer is, well, sort of, right? The elements of this look like this, right? It's some element of A followed by some element of B cross C, which is just going to be a pair of some element of B and some element of C. On the other hand, over here, we have a pair of some element of A cross B, right? So that's going to be a pair, something from A, something from B, comma, an element of C. And so these aren't quite the same thing. But again, we can just kind of match them up. I mean, they're pretty much the same thing. They just have parentheses in different places. And oftentimes this reworking of parentheses isn't going to make a difference, right? If these are, if we're trying to talk about vectors, right, we're essentially, in either case, talking about the vector ABC. It's just that we have slightly different notations for referring to it. And so there's a sense in which we want to call these sorts of elements of these sorts of structures, we want to call them A, comma, B, comma, C, and we want to say that that's part of a structure A cross B cross C. Right? We can generalize our Cartesian product notation to be able to refer to not just pairs, but also triples or quadruples or whatever, where the first element is some element of the first set, and the second element is some element of the second set, and the third element is some element of the third set, and so on and so forth. And these all wind up being equivalent to each other. So this is another reason why I think it's really nice to use multiplication notation for the Cartesian product, because it sort of satisfies the properties that multiplication satisfies. It sort of satisfies commutativity, usually, kind of, and it usually satisfies associativity. Again, sort of. Now, a question you might ask is, if we're going to use multiplication notation for the Cartesian product, can we make sense of addition notation? And a good first guess would be to use addition to refer to the union of two sets. But that's not quite right. If I take, for instance, the sets 2 and 3, when I take the union of these two things, it's going to be just the set 0, 1, 2 again. It's just going to be 3. And that's not what we want. We want it to be the case that when we take the addition operation, whatever that is, and combine the sets 2 and 3 together, we at the very least get a set of size 5. Now, one way to resolve this is to kind of mark these elements separately. What I'm going to do is I'm going to color the elements of the first set red and the elements of the second set blue. And so now they aren't going to merge together when we take the union. This red 0 is different from a blue 0, and so they're not going to merge together, which is what we don't want. What I'm going to wind up getting is this 5-element set here, which is exactly what we want. We want it to be the case that when we take the union of a 2-element set and a 3-element set, we get a 5-element set. And the question is, how can we formalize this? We don't usually color the objects in mathematics. What we're instead going to do is construct pairs, right? The actual element from the set that we were interested in, either an element of A or an element of B, followed by a marker. This is kind of the thing that corresponds to the color we had before, that tells us whether it comes from the first set or the second set. And this construction here, or constructions that essentially accomplish the same thing, are called disjoint unions. Now, this is kind of the iffiest part of this video because this isn't common notation for the disjoint union. More often, I've seen a union symbol with a dot over it, or a square union symbol, or sometimes a union symbol with a plus sign in it for the disjoint union. And I've also often seen the addition symbol meaning something different when combining sets in algebra. It's very rarely the case that when we have two vector spaces or two groups or two rings or two fields, and we take their disjoint union like this, that we actually get a vector space or a group or a ring or a field. And so actually more often in algebra, this notation is used to represent kind of the span of these two sets. And this is more often the sort of thing that we actually want to study in algebra. And just to do a quick example, 2 plus 3, again, 2 represents the set 0, 1, and 3 represents the set 0, 1, 2. In this notation here, 2 plus 3 represents the set of all pairs. An element of 2, either a 0 or a 1, followed by a 0 to indicate that it was from the first addend, right, from this set here, or it's going to be an element of 3, a 0, a 1, or a 2, followed by a 1 to indicate that it's from the second addend of the sum. And again, this set here isn't the set 5, but it's a set of size 5, which is what we were looking for. And now, of course, the question, does this notation satisfy the kinds of properties that addition does? Is, for instance, a plus b the same, roughly, as b plus a? And well, the elements of a plus b are going to be an element of a followed by a 0, or an element of b followed by a 1. The elements of b plus a are going to be elements of b followed by a 0, or elements of a followed by a 1. And again, these aren't quite the same thing. We're going to wind up having trouble when we talk about linear orderings, for instance. But just the sets, right, we can just match these elements up with these elements and these elements up with these elements. And it's essentially the same thing. I'll let you think about the question of associativity. But now, the really interesting question is, are these two notations compatible with each other? For instance, do we have something kind of like distributivity? The elements of A cross B plus C are going to be pairs. The first element is just some element of A, followed by some element of the disjoint union of B and C. That is either an element of the form B comma 0, or an element of the form C comma 1, where B is from B and C is from C. So these are the sorts of elements we can expect to see in this set. And then in this set, well, it's going to be some element of A cross B, comma 0, or some element of A cross C, comma 1. Well, the elements of A cross B are just pairs, A comma B, where A is in A, B is in B, and the elements of A cross C are just pairs, AC. And so again, we get this very natural correspondence. These elements are almost exactly the same as these elements. The parentheses are just slightly different. So we can make these elements correspond to each other, and these elements correspond to each other. So there really is a sense in which the disjoint union is the addition to the Cartesian product's multiplication. But again, be careful, this notation isn't actually that common. It's used a lot when studying linear orderings and graphs, but it's not very common to use this sort of notation in algebra. Now, you might wonder, can we go a step further? Can we define exponentiation, right? Some notion of if a and b are sets, what should a to the power of b mean in a way that's compatible with having the Cartesian product be multiplication and disjoint union be addition? And the answer is yes. We should let a to the b denote the set of all functions from b to a. So the first thing that we want to check to make sure that this is a sensible notation, it agrees with what we've been doing before, is that it should respect the sizes of sets, right? If I have a set of size 2 and raise it to the power of a set of size 3, I should get a set of size 8. And sure enough, if we look at the set of all functions with domain 3, so domain the set 0, 1, 2, and range 2, the set 0, 1, there's 8 of them. More likely than R cross R, you've probably seen the two-dimensional real vector space be denoted as R2. And this, in this notation, means the set of all functions from the set 0, 1 to R. And this is slightly different, but there's a natural correspondence between these things, right? A function that takes in either 0 or 1 and outputs a number R really only has two things that we need in order to specify it, right? We need to specify what f of 0 is, and we also need to specify what f of 1 is. And one way you could specify this is just as a pair, f of 0, comma f of 1, or as a vector. And these two presentations are essentially the same. For instance, the notion of what it means to add two functions together, right? F plus g of 0 is just going to be f of 0 plus g of 0, and f plus g of 1 is just f of 1 plus g of 1. And similarly, if we write it out like this, the first coordinate, f plus g of 0, is going to be, well, it's going to be f of 0 plus g of 0, the first coordinates of the addends. And similarly for these other cases. So there really is a sense in which we can identify vectors in two-dimensional space as just functions from the set 0, 1 to R. And again, similarly, if you've seen the notation r cubed to indicate three-dimensional vectors, triples of real numbers, well, again, you can represent them as functions from the set 0, 1, 2 to R, where, again, it's just going to be the case that this represents the vector f of 0, f of 1, f of 2. Another application of this notation is when we write something like 2 to the omega. This is the set of all functions. This is the set of all functions that take in some natural number and output either a 0 or a 1. And we can identify these with infinite sequences of zeros and ones. And similarly, if we replace the 2 by the real numbers, we're just looking at the set of all functions that take in as input some natural number and output a real number. And again, we can view these as corresponding to infinite sequences of real numbers. While we're here, I'd like to point out another piece of notation that's kind of along these lines. I've seen the notation r to the less than omega to indicate the set of finite sequences of real numbers. And you can change r to be whatever set you want. I've also seen r to the less than infinity for this, or if you're feeling automata theoretic, r star, the set of words on real numbers. Now, of course, the big question, is this notation compatible with these notations here? For instance, we might want it to be the case that a to the b plus c and a to the b cross a to the c should correspond to each other naturally. As usual, they won't be equal to each other, but there'll be a natural correspondence between these two. Here we have functions that take in an element of the disjoint union of b and c and output an element of a. In other words, these functions, well, they're going to take in pairs of the form b comma 0 and output some a's for those, and pairs of the form c comma 1 and output some a's for those. What we have over here are pairs of functions, g comma h, where g takes elements of b and outputs elements of a, and h takes elements of c and outputs elements of a. And there's a natural correspondence between these. If we have some pair g comma h like this, we can turn it into some f over here. We say that if we see an element of the form b comma 0 as input, we should output g of b. Right? G takes in elements of b as input and outputs elements of a. We have an element of b, we want an element of a, and this is exactly how we can get that. And similarly, if f sees a pair of the form c comma 1, well, we have an element of c, we'd like an element of a, we have our h, so we just return h of c. And you can reverse this process to, given a particular f, construct the corresponding g and h functions. And so we see that these two sets really do correspond to each other, leading us to believe that this really is good compatible notation with the cross product as multiplication and the disjoint union as addition. Another question we might ask is whether or not there's a correspondence between functions from b cross c to a and functions from c to functions from b to a. If we have an element of this, it's going to be some sort of function f that takes in pairs of an element from b and an element from c and outputs an element from a. And over here, we're going to want some sort of function g that takes in an element of c and spits out a function. So g of c is going to be a function that takes in elements of b and spits out elements of a. And so what we have here are two different ways of feeding two inputs into a function, one from b and one from c, and getting as output some element from a. And so there's a natural correspondence between these two. You just kind of shuffle how the inputs are inputted. So thanks for watching. I find this notation really compelling just because of how nicely it fits together with itself and also with some notation that we're already familiar with. But it's important to keep in mind that not everybody uses the same notation. If you're reading some piece of mathematics, be sure to check out the notation being used in that piece of mathematics. And if you're writing mathematics, be sure to be clear about what the notation that you're using means. Please leave any questions or comments that you might have down below, and also please share some notation that you think is really neat. And be kind to each other.